Hello dear students. So in continuation to our discussion, in the last class we have discussed what is an acoustic wave and how we can get omega versus k for an acoustic wave. So the point is, we have realized that the type of wave which propagates through the plasma in the absence of any collisions is nothing but an acoustic wave which has a velocity, or let us say we call Vp is square root of gamma p naught by rho naught. So in this class we will try to understand what is an ion acoustic wave and how we can get the dispersion relation for that. So the topic is ion acoustic wave. So it has been found that the ions can transmit vibration when they are vibrating because of the pressure perturbation. They can transmit vibration in the absence of any collisions because of their charge. So in the earlier picture we have made the collision terms mn u minus u naught by tau to be 0, but in the absence of collisions also there is a possibility that the ions can transmit the vibration by the virtue of their charge, because they have some charge, right. So the interaction happens in the presence of an electric field. So electric field is generated because of their charge, right. Since the ions are heavier, we can still say that the resulting waves will be very slow frequency oscillations. So the frequency of oscillations is considered to be small because of the heavier mass of ions. We will still confine ourselves to the no magnetic field situation, and we will also assume that the number of electrons will be always equal to the number of ions. So the two equations that we require are, we can write, so dou Ni by dou T plus del dot Ni Ui is equal to 0. Right. So let us say this is equation number 1, and for the ions we can write the momentum equation as rho I, the density of ions, times dou Ui by dou T plus Ui dot del times Ui is equals to Qi Ni Ei minus del P. So we still have this pressure force term on the right hand side, but in addition to that we have now introduced the force due to the electric field. Where is this electric field getting created? This is representing the charge of ions, or we have assumed that the vibration of the ions, the information about the vibration of ions is well preserved or well represented by the electric field. So we know that del P or is gamma P del n by n, or using P is equals to n kBt, you can use P is equals to n kBt. We can write del P as gamma kBt del n. So depending on ions you can use ion temperature, or for electrons you can use the electron temperature. So we can rewrite the equation for the ions as rho I times dou Ui by dou T plus Ui dot del times Ui is equals to Q Ni E minus gamma kB Ti delta n. Okay. So we can write the electric field E as the gradient of the potential. We know this very well, right? So what have I done? I have just written the two equations which are relevant, the continuity equation and the momentum equation. I have rewritten delta P so that it represents temperature as well, and the variation in the number density of the charged particles del n and Ti, and then I am trying to write the electric field in the units of a potential. Right. So, we can simply write it as rho I Let us say we call this form of the equation as equation number 2. Both are same, but written in terms of parameters that we are going to use it. So, we can write a similar expression or similar equation for the electrons, which is ME NE times dou UE by dou T plus del dot UE times UE is equals to minus E NE del phi minus gamma KB TE del n. So, for very small or very slow ion vibration, the electron mass can be regarded as 0. What does it mean? It means the electron inertia, the mass of electron is very small in comparison to the ions. Ions themselves are moving very slow. So, we can neglect the electron inertia, and we can also neglect the advection term, which has a second order velocity in it. Right. So, we can make this to be equal to 0, and we can also make this to be equal to 0. So, in that case, what we will be left with is E NE del phi minus gamma KB TE del n is equals to 0. Right. Now, for slow ion waves, the electrons move very fast and they equalize the temperature among the entire plasma. Thereby, you have an isothermal picture, and if it is an isothermal picture, you can take the gamma E or the ratio of specific heats to be gamma E to be equal to 1. When is this valid? This is valid only when you have a perfectly isothermal condition or the environment. The assumption is the electrons, because of their small mass, they will move around and they will equalize the temperature. They will bring the temperature into an equilibrium. Right. And if we consider only one dimensional case, we can write E NE dou phi by dou x is equals to KB TE dou NE by dou x. E dou phi by dou x is equals to KB TE by NE dou NE by dou x. And if we integrate both sides, integrating both sides, we can write E phi integrate with respect to x. E phi is KB T ln NE plus C. Right. So, we are now getting a form of the potential that we that is responsible for the electric field. Now, let us say at equilibrium situation, at equilibrium, we impose that NE is equals to N naught, and without any vibration, and at equilibrium or at the beginning, let us say, without any vibration. So, when things were not set into motion, without any vibration, we can simply write the phi is equals to 0. So, these can be considered, these two conditions can be considered as the initial conditions for the plasma. In that case, we can write, putting these two things back into the equation, we can write we can get the value of C, which is equals to KB TE ln N naught, the undisturbed number density is equals to minus C. Substituting this back into this equation, so we call this as this is 3 and this is 4. So substituting the value of C, substituting the value of constant C into equation number 4. What we will get is E phi is equals to KB TE ln NE minus KB TE ln N naught, or E phi is KB TE ln NE by N naught, or we can write NE is N naught exponential E phi by KBTE. This expression of course looks familiar, right? So, this expression says that the electrons are distributed according to the Maxwell's distribution. So, Maxwell distribution is imposed onto the electrons. So, if everything that we have considered, all the assumptions that we have considered, if all of them were to be true, then the electrons have to be distributed according to this distribution function, which is the Maxwell distribution function. Now, we will make one more assumption saying that the perturbations to be very small relative to the thermal energy, just to keep things simple. So, perturbations or the potential that comes out because of the perturbations is very small in comparison to the thermal energy that is there inside the plasma. So, in that case, so this numerator E phi becomes very small in comparison to KBTE. So, we can write the exponential or expand the exponential just so that only the first two terms matter to us. So, NE is N naught will be approximately equal to NE is equals to N naught into 1 plus E phi by KBTE. What does this mean? Just look back into what we have done. We have taken the ion momentum equation and we have made the mass of the ion negligibly small in comparison to the mass of ion. So, we can neglect this term and it will be sufficient to say this, but still the velocity, the second order term, velocity term is also neglected, and so we have all the right hand side becoming equal to 0, which gives an idea that how we can evaluate del phi out of this. So, this equation, if it has to be true, we will say that the electrons are moving randomly or with around the plasma, and they are bringing the temperature to an equilibrium value. So, that means that we have an isothermal condition, constant temperature condition. The isothermal condition imposes gamma E to be 1. Using that, we can get a form in which the potential can be written. So, we have this constant C, and in order to evaluate the value of that constant, we consider equilibrium. At equilibrium, NE, the number of electrons, is equal to the equilibrium value of N naught, and in the absence of any vibrations, because the vibrations are the ones in which the information about the electric field constituted by ions is transmitted. So, by the virtue of its charge, because there is charge, so this information is transmitted. So, if without any vibration, we will say that this electric field, which is constituted out of potential, will automatically become 0. So, phi is taken to be 0, and when you take phi to be 0, you write this KBTE ln N naught is equals to C, and substituting the value of C back into this equation number 4, we get this. So, this will give you an empirical expression for phi, which is KBTE ln NE by N naught. So, thereby NE can be written to be N naught times exponential E phi by KBT, which says that the distribution that the electrons are following is Maxwellian in nature. And to simplify things further, we say that the potential that is there is very small in comparison to the thermal energy. That means, if the potential is being used to accelerate the electrons across this potential, they will not gain much energy in comparison to the thermal energy that they possess already. So, in that case, the exponential can be truncated to the first two values, which is n naught into 1 plus E phi by kBTE. Right. Now, let us say the perturbation electron density is also equal to the perturbation in ion density. Where is the perturbation actually coming into picture? The perturbation is coming into picture because we want a certain type of wave activity to happen. So, if the ions are vibrating around their mean positions, just so that they can transmit a pressure pattern through them. Then let us say if we consider a simple case, how the pressure is being transported, how the pressure fluctuation is being transported. So, we can consider a fluid inside a tube, let us say, and we fix a diaphragm at the end. What is the diaphragm? This diaphragm is able to oscillate back and forth. Okay. Now, let us say if the diaphragm is pushed inside, what happens to the fluid? The fluid is pushed in like this, right. Now, if the diaphragm after a period of time or immediately when it kinds of comes back, the diaphragm is extending out like this. So, now the fluid is being pulled here outside or outward, right. So, what is happening in this picture? So, as the time progresses, as the diaphragm is vibrating back and forth, we can see that, let us say, after a certain point of time, the diaphragm is extending out, then we can see that the molecular vibrations effectively transport a pattern of high and low pressures inside the fluid. So, this is obviously a high pressure, and this is obviously when they are extending outside, you have a low pressure, right. So, as the time progresses, what are the molecules? The molecules are just vibrating around their mean positions. They are not being transported directly into the column of this tube, because you are not supplying any gas inside. So, you are just vibrating the diaphragm. So, while it vibrates, alternate patterns of high pressure and low pressure are being transported into the fluid column, right, like this. So, this pattern is simply a pressure fluctuation which is being transported into the fluid. So, this is what I was talking about. Now, we will say that the perturbation, because you consider the mean position, the electron density or the ion density will vary for a moment due to this vibrations, right. So, this will make an assumption that the perturbed ion density and the perturbed electron density are equal in number. So, they will say that Ne is N0 plus N1, right. This is how we write it. Okay. Now, for the N1 electron, let us say, is Ne minus N0, right. But we know that N0, Ne, we know that Ne is N0 plus N0 E phi by kBT. We have a minus N0. What am I using? I am using this. You see this? This is the Ne. I am using this Ne into this equation as this minus N0 as it is. So, we can write N1E, the perturbed electron density, as simply N0 E phi by kBT. Now, interestingly, we see that the perturbed electron density is a function of this potential phi. Let us say we say that N1E, because we said perturbation in electron density is equal to the perturbation in ion density. So, we make it equal to N1I. This is because of this simple assumption, perturbation in electron density is equal to perturbation in ion density. Fine. So, as a result, what do we have? We have a very important equality, which is N1E is equals to N1I. Let us see how we use it. Okay. Now, we have established the basic equations that we require, and also the variables which we think will be perturbed due to the wave activity. So, we write the perturbed variables as N as N0 plus N1 without using the suffixes for electron and ion, and U is U0 plus U1, and phi is equals to phi 0 plus phi 1. Okay. Now, we will consider neutral plasma, which is in equilibrium, which imposes the fact that U is equals to 0 to begin with, and phi is equals to 0 to begin with, the initial values basically, and delta N0 is 0. And since we are using the linear perturbation theory, we can simply write dou N0 by dou t is equals to dou U0 by dou t is equals to dou phi by dou t is equals to 0. All the initial values are constants in time, so we do not have to worry about them when we linearize the equations. Right. So, now substituting these perturbations into the ion momentum equation and the ion continuity equation. So, substituting, let us say we call this as equation set A, substituting equation set A in ion momentum and continuity equations. So, I am writing all these things because it will develop a sense of continuity, and it will be easy for you to flow, edit here, it will be easy for you to follow the algebra that I am doing, right. So, we will write dou N1 I divided by dou t plus del dot N0 plus N1 I times U0 plus U1 I is equals to 0. This is the continuity equation for ions. Okay. If we expand it, we will write dou N1 I. I have already made one term 0 before I write this, and del dot N0 U0 N0 U1 I N I1 U0 N1I or U1I is equals to 0. N1I or Ni1, both of them are same. So, this term N0 U0, which is a product of equilibrium terms, of course, can be made to be 0. We don't want that. And this one is this one, yeah, this one is a second order term in perturbation, so it has to be 0, and N1I perturbation term multiplied by an equilibrium velocity, and we have considered the initial velocity to be 0. So, we have to make it 0, right. So, you see this condition is being used here. The initial velocity U0 is 0 when things are not set into motion. Okay. So, using this in combination, we can now write, we have only one term out of the 4 terms that are appearing in the right hand side of the continuity equation, or the second term in of the continuity equation, n naught u I1. Okay, we will write dou n1 I by dou t plus n naught times del dot u 1 I is equals to 0. So, what is the equation number here? Equation we used, let us say we call this as 5, and this is equation number 6. Okay, so we will continue this class by applying the perturbation into the ion momentum equation in the next class.